Chemistry, Chapter 20, Video 5, Electrode Potentials. So you know what potential is. There is a potential difference if there is a higher charge somewhere in comparison to a lower charge somewhere else, which are connected in some form of a mechanism. Now, if two chemically related species means, for example, copper 2 ions and copper. If they are in different oxidation states, right? So if they are in contact with one another, if a copper piece of metal is placed in contact with copper ions, there will be a equilibrium that would establish between copper ions and copper. So what happens is Cu2 plus will gain 2 electrons to produce copper, and then copper will lose 2 electrons to produce copper ions. So there are two reactions that take place simultaneously. What are they? Copper ions gaining 2 electrons to become copper, and then copper ions gaining electrons to become copper, and copper losing electrons to become copper ions. So those two equations are taking place at the same time, right? So the redox equilibrium is reached when the rate of electron gain is equal to the rate of electron loss. But the equilibrium will be either further to the left, or it is not going to be exactly at the middle. Could be at the middle, but it is very likely to be it would shift to the left or right, depending on the circumstances. Now, when you talk about copper, it is a rather unreactive metal, right? When you compare it with other metals, usually in copper, the equilibrium lies further to the right. Further to the right means there are more there are more of copper, right? There are more of copper. So copper ions are easy to reduce. They gain electrons readily to form copper metal, but copper is not very likely to become copper ions. So that is why reactivity is kind of low, right? So I hope you understand that. Then for reactive metals such as vanadium, the equilibrium lies further over to the left. That means there are more ions than vanadium metal. Vanadium ions are therefore relatively difficult to reduce. They gain electrons much less readily by comparison. The position of equilibrium differs for different combinations of metal placed in solutions of their ions. When a metal is put into a solution of its ions, an electric potential or voltage is established between the metal and the metal ions in solution, right? So there is a potential difference that develop between the metal and the metal ion in solution, right? The reason is because they are either because the equilibrium would be further to the left or further to the right. We cannot find this potential directly. We have to develop a certain system, metal and metal ion system, and join it with another system to find how the electrode potential is developed. This electrode potential is represented by capital E and is obviously measured in volts because it is potential. And the standard cell that we use to compare this, the standard system that we use is the standard hydrogen electrode. So if you use standard hydrogen electrode in comparison, or to compare how the E changes, or the electrode potential changes in another system, we will get certain values in comparison to this hydrogen electrode. So this will give us a reading in relation to E, right? You will understand how more details when we go by. It is thought that the absolute electrical potential that we cannot measure are caused by the formation of an electrical double layer when an element is placed in a solution of its ions. For example, when zinc is placed in a solution containing zinc ions, a tiny number of zinc atoms on the surface of the metal are converted to zinc ions. So what basically happens is here, now as you can see in this diagram, here the zinc is placed in zinc sulfate solution. The zinc rod is placed in zinc sulfate solution. Then what happens is a tiny number of zinc ions actually covers the surface of the zinc metal, leaving zinc ions on surface. Right? There are excess electrons. Now the surface of the metal surface surface atoms convert into zinc ions by losing electrons. So there are more electrons on the surface and they get attracted to these zinc ions, right? Because positive and negative get attracted. So now an electrical double layer, that is the electrons on the surface and zinc ions close to that, gets they come and form an electrical double layer. There is a buildup of charge. This is what that creates the electric potential between the metal and the metal ions in solution, because there is a positive and a negative charge build up there, as you can see in the diagram. So that happens. As a result, we say that an electrode potential is developed. I hope you got a basic idea. They will not ask you questions out of how it is developed, but rather they will ask you more practical details about the electrode potential. Write down a note. Electrode potential. An equilibrium exists between two chemically related species that are in different oxidation states. For example, write this equation: Cu2 plus aqueous plus 2E, equilibrium sign CuS. Both forward and backward reactions take place at the same time, but because copper is a rather unreactive metal, the equilibrium would be further to the right. When a reactive metal such as vanadium is considered, the equilibrium will be further over to the left and ions will be harder to be reduced. Leave line and right. When a metal is placed in a solution of its ions, a potential difference builds up due to the charge accumulated by the electrons and the ions they produce, within brackets, right, electrical double layer, and this potential that is developed is known as electrode potential, within brackets, E, capital E. However, this potential cannot be found directly. But can be found using another system connected to it. We usually use standard hydrogen electrode for this purpose. Please draw this separation of charges diagram, this figure 20.4. You will understand it better. If you have any further questions, please raise them. We will go to the standard hydrogen electrode in our next video. Thank you.